Okay, good afternoon everyone. Welcome to this IMechE seminar on the thermal management of fuel cells for transport applications. My name is Alistair Cairns and I'm a professor in mechanical engineering at the University of Nottingham and the current chairman of the IMechE Vehicle Thermal Management Systems Conference. This conference is usually held every 2 years and actually around about this time of year. Due to COVID, we opted to present a seminar this year in place of the physical conference, but I'm pleased to say that there'll be a face-to-face conference this time next year. So please do keep an eye on the IMechE website for details of that. At the last count, there was over 600 attendees planning to attend this seminar. Which was really excellent to see and reflects the high interest that there is at the moment in hydrogen as part of the mix for decarbonised propulsion as we move forward, especially for larger vehicles. And from a thermal management stance, the fuel cell has obviously significant challenges, both under cold start conditions, particularly sub-zero, but also at high loads where the inefficiency in the fuel cell manifests itself as low-grade waste heat. And actually that brings unique challenges and opportunities at a vehicle level. And I'm pleased to say we've got some excellent presentations lined up today that are going to address some of those opportunities. So before we go into the list of speakers, there is some housekeeping to deal with. Firstly, as attendees, you're automatically muted and off camera. But please do feel free to use the question box throughout the presentations to ask any questions. We'll deal with some of those questions by written answers during the course of the presentations, but we'll also have a panel session at the end of the seminar to give you an opportunity to ask any additional questions live. Secondly, we do need to inform you that the session is being recorded and it will be available to download later on through the IMechE website. So that's the housekeeping dealt with. So we can now move on to the good bit, which is the technical presentations. So if we could just move to the next slide, thank you. So as you can see, we've got 4 excellent presentations lined up, and our first presentation is entitled Fuel Cell Mobility. So Toyota Strategy and Thermal Challenges. And this will be presented by Nick Buyens, who is a technical expert in model-based design at Toyota Motor Europe over in Belgium. So Nick graduated from the Free University of Brussels as an electromechanical engineer with a master's thesis on simulation methods for vehicle thermal management. Since 2013, Nick has worked on thermal management projects in the Powertrain group at Toyota Europe, covering a variety of fields, including heat damage, powertrain and cabin warm-up, coolant and refrigeration systems, and FCEV energy management. His work focuses on simulation methodology, but also covers physical testing and pre-development work. And as of 2019, Nick is also responsible for the simulation development team at Toyota, which supports the fuel cell business unit in commercializing fuel cells, not just in passenger cars, but also across trucks, buses, and stationary power generation. So I'll now pass you over to Nick for his presentation.
Hello everyone, my name is Nick Buyens. I am an engineer in the Powertrain group at Toyota Motor Europe, and today I will introduce to you the Toyota strategy and thermal challenges of fuel cell mobility. Today's presentation contains 3 main items. The first is an introduction to Toyota fuel cell strategy. The second, an introduction to fuel cell fundamentals. And the third, a bit of a deep dive into fuel cell thermal challenges. In terms of environmental challenges, Toyota has made a challenge to aim towards sustainable operations, products, and a society by 2050. One of these challenges is to look at the vehicles that we produce, and Toyota's commitment is to have carbon neutrality globally by 2050. In order to achieve this, we need to invest in the next generation vehicles, which means hybrids, plug-in hybrids, fuel cell electric vehicles, battery electric vehicles. Toyota's view of the mobility roadmap is that multiple technology solutions are necessary to achieve our sustainability targets. In terms of vehicles, we can separate the vehicles by vehicle size and distance or operation in usage. And here we can see that Toyota believes different technologies are suitable for different groups of vehicles. In terms of fuel cell, Toyota believes that fuel cell is ideal for more heavy and long distance applications, but also high usage applications such as forklifts. In Europe, Toyota is aiming to create a hydrogen society. And in order to do that, we are relying on three strategic pillars. The first is the rollout of fuel cell technology through the Mirai passenger car sales. The second is the rollout of fuel cell technology through commercialization of Toyota fuel cell systems to third parties. And the last pillar is the creation of a leadership position in the hydrogen society. So not only focusing on the fuel cell technology, but actually considering the entire hydrogen ecosystem. Toyota has over 28 years of fuel cell development, starting in 1992 through several prototypes. In 2015, we finally arrived at the first mass production fuel cell vehicle, which was the Mirai. And of this vehicle, almost 11,000 vehicles have been sold globally. In 2020, the second generation Mirai was introduced to further roll out the fuel cell technology of Toyota. Toyota is heavily involved in fuel cell and invested in fuel cell. We are continuously ramping up our production volumes. We have invested heavily in new production facilities and new production lines for fuel cells, fuel cell tanks, and other components. This has allowed us to move our production from 3,000 units per year for the first generation Mirai to 30,000 stacks per year in 2020. And this production volume is not only the fuel cell in the Mirai, but also the fuel cell that is used in commercial projects with third parties. For the third generation fuel cell, we are aiming to have even higher production volumes. Fuel cell system applications can cover not only passenger cars, but also other industries in the mobility and transport sectors. We know that the regulations for emissions and carbon output are getting more and more strict for all kinds of industries. And Toyota believes that fuel cell is a versatile technology suitable for various applications. In terms of examples, we can see here on this slide several applications of fuel cell technology from Toyota in different industries. We can also see that Europe is heavily involved in several of these projects to roll out the fuel cell technology. Next, I will do a brief introduction into the fundamentals of how a fuel cell operates. From an electrochemical point of view, the reaction of the fuel cell that we are using in our vehicles and in our stacks is very simple. We start with hydrogen fuel that enters the anode side of the fuel cell. It goes through a gas diffusion layer into the catalyst on the anode side, where the hydrogen is split in electrons and protons. The protons can move through the membrane to the cathode side, but the electrons have to move through an electric load in an external circuit, which is generating an electrical power. The electrons, the protons, and oxygen join at the cathode side, where they generate water and heat. The electrochemical thermodynamics of this simple reaction are well known. We can easily calculate the maximum reversible work that is able to be generated out of this reaction. And from this maximum reversible work, we can calculate the ideal electrochemical efficiency of the fuel cell reaction. The fuel cell reaction that we are considering has an efficiency of 83% in ideal conditions. As a reminder, this is much higher than an internal combustion engine, which has an ideal thermal efficiency of less than 60%. We can also relate the energy that is produced in this reaction to a potential through the electrochemical laws. So we can see here that the maximum ideal potential that a fuel cell can generate is 1.23 volts. However, if we were able to somehow translate the whole energy released by the reaction into a potential, we would reach 1.48 volts. The difference between the two voltages is of course 83%. In terms of fuel cell performance, we usually use what is called an IV curve, which plots the cell current density versus the cell voltage. This is very similar to an internal combustion engine torque speed map. On this slide, we see the example IV curve of a fuel cell. We can see the thermal voltage in red, the reversible or ideal voltage in green, and in the black line we see the actual fuel cell voltage. As we can see, the black line is significantly lower than the green line, and this is due to some losses that occur in the fuel cell system, which means that our fuel cell cannot achieve the ideal voltage. These are OCV losses, open circuit voltage losses, activation losses, ohmic losses, these are very similar to a battery, and at the end, mass transport or concentration losses, where the fuel cell starts to lose power because the gases cannot be supplied fast enough to sustain the reaction. Looking at this graph, we can identify certain things. As we know, the electrical power is simply the voltage multiplied by the current. If we have an operating point, which is the black dot in the middle of the graph, the surface under the voltage curve is actually the electrical power generated by the fuel cell. The surface above the voltage curve and between the thermal and the voltage curve, that is actually the heat that is generated by the reaction. By looking at this relationship, we can actually easily calculate the fuel cell efficiency, the real fuel cell efficiency, by simply relating it to the fuel cell voltage at any operating condition. The heat generated by a fuel cell needs to be dissipated similarly to an internal combustion engine. This goes in two main paths. The first is through the exhaust, so we can use this heat to partially evaporate the water generated by the fuel cell, but we can also have the heat go into the structure of the fuel cell, which then needs to be transported away either by diffusion to the ambient or by coolant circuit that runs throughout the fuel cell. Next, we will highlight certain thermal challenges that fuel cells face. The first main topic of challenges is related to heat rejection. The fuel cell has a certain cooling requirement, and this is different than an internal combustion engine. So let's have a look at a generation 1 fuel cell in a Mirai and a 2-liter turbocharged engine from a Lexus NX. In this table, you can see the operating point, which is 50 kilowatts of useful power. So useful power for the fuel cell is electrical power. Useful power for the internal combustion engine is mechanical power at the crankshaft. Here we can see that the fuel cell has a higher efficiency than the internal combustion engine. But what we can also see is that the fuel cell emits most of its heat into the structure of the fuel cell and only a small portion into the exhaust. Whereas for internal combustion engine, a large portion of the heat generated by combustion is evacuated through the exhaust. If we then look at the second operating point, for example 115 kilowatts, we can see that still the fuel cell is more efficient than the internal combustion engine. However, because the heat is mostly absorbed by the structure of the fuel cell, the coolant needs to transport a lot more energy away from the fuel cell than in the internal combustion engine. So in this case, 40% more heat is being put into the structure of the power plant compared to the internal combustion engine. As a solution, we need to ensure a high surface area cooling channel within the fuel cell stack and have high coolant flow rates to evacuate this heat. The second challenge in terms of heat rejection is regarding the radiator performance. A radiator can be simply estimated as the power being proportional to a factor and the temperature difference between the coolant and the air going onto the radiator. Because a fuel cell operates at a lower temperature than a combustion engine, the delta T between the coolant and the air is smaller for a fuel cell. And we can see on this graph, for different ambient temperatures or air temperatures, the fuel cell will operate with the same radiator at the same coolant flow rate and the same airflow rate at a much lower power than for the combustion engine, because the combustion engine can achieve 20-25 degrees higher coolant temperatures. As a solution, we need to increase radiator sizes to achieve the same cooling power, we need to increase the airflow rate on the radiator. We need to increase the coolant flow rate through the radiator. A third item for heat rejection is the efficiency degradation of a fuel cell. The challenge is that the fuel cell performance is not steady throughout its lifetime. The efficiency of the fuel cell degrades slowly as the fuel cell ages. And here on this graph, you can see in the black line an IV curve of beginning of life fuel cell, and in the red line an end of life very aged fuel cell, which has a 20% efficiency drop. You can also see in the dotted lines the power curves for the two conditions. If we consider a certain operating point, for example indicated by the black dot, we have a certain heat generation that is associated with this operating point. If we want to achieve the same power at the end of life, we need to increase the current, which then leads to additional losses, which leads to a load point shift further down on the IV curve. And of course, this means that we have an additional heat generation that accompanies this load point shift. So as we can see here, in this fuel cell, we have a 20% efficiency drop, but we actually have a 60% additional heat generation compared of the end of life and the beginning of life. And this is due to this compounding effect of the losses needing more current, leading to more losses in the fuel cell. As a solution, we need to have a proper hybridization strategy or fuel cell usage strategy to minimize this efficiency drop over the lifetime of the fuel cell. And secondly, we need to have an appropriate radiator design that considers the entire fuel cell lifetime of our application. The second challenge for fuel cells is cold conditions or freezing conditions. In this example, we see the water buildup that occurs in a fuel cell. So on the right side, we see a fuel cell with the hydrogen-oxygen channels. And if we zoom into this oxygen channel, we see that oxygen moves through this channel, but water is being generated in the fuel cell and needs to be evacuated. This water goes into the oxygen channel and is moved away through the oxygen flow. However, there are ribs in these channels, and water can be stuck in the gas diffusion layers below the channels, which then, when we park the car during freezing conditions, could lead to ice forming within the fuel cell. This ice will then block the flow of oxygen after starting again. So as a solution, we can actually improve the oxygen flow inside of these channels, which will then allow us to move water away during operation. But we also have active water management during driving and a purging before and during parking. So as you can see on the graph on the bottom left, after we stop the car, a shutdown purge is operated, which basically flushes the system by moving a lot of air through the system, which then removes the excess water. However, some water is still remaining in the fuel cell as it is needed for the efficiency of the fuel cell. Therefore, when the system recognizes that we are close to the freezing temperature, which is 0 degrees, an additional parking purge is initiated, which will further remove any water to avoid freezing in the fuel cell. The second channel is water generation during operation of the fuel cell below freezing. So as you can see here, we have an image of the channels at minus 10 degrees. As the fuel cell is operated at minus 10 degrees, water is generated as supercooled water. So this is a liquid form. However, after some time, the supercooled water freezes, which blocks the cathode channels and blocks the oxygen flow. This could lead to starvation of the fuel cell. Therefore, as a solution, we can operate the fuel cell in a low efficiency point. So here you see the operation of the fuel cell in a normal condition. We can artificially starve the fuel cell with controlled oxygen starvation, which moves the curve of the starvation line. And we can then operate at the same isopower point further down in the efficiency band, which will lead to the same power generation, but with a higher heat generation. And this causes a rapid heat up of the fuel cell. In terms of cold start performance, here we can see an example of a vehicle parked at minus 20 that was parked overnight and reaches as low as minus 30 degrees. And in this example, the vehicle was started and the driver aggressively starts to accelerate and decelerate. And we can see that the fuel cell system was able to warm up completely after 70 seconds, which is very comparable to a combustion engine. As a conclusion, Toyota believes that fuel cell technology can help to achieve carbon neutrality in the entire transportation sector, not only passenger vehicles, but also trucks, trains, buses, aviation, shipping, and so on. But fuel cell vehicles are faced with a new set of thermal challenges compared to other vehicle types. So Toyota will continue to invest strongly in world-leading fuel cell technology to overcome these challenges, but we also rely on strong partnerships with our suppliers to come up with solutions for these issues. This concludes my presentation. Thank you for your attention, and any questions will be handled in the Q&A at the end of the session.
So thank you very much, Nick, for a very informative presentation and an excellent overview of some of the fundamental challenges with fuel cells. So now we'll move on to our next presenter. If we could go to the next slide, please. So the next presentation is entitled Challenges and Solutions for Fuel Cell Vehicle Thermal Management Systems. And the presenter is Neil Fraser, who is Head of Engineering at MAHLE Powertrain, Germany. So since 1996, Neil has worked at MAHLE Powertrain, which is formerly the road parts of Cosworth, in a range of different roles, with main focus on gasoline engine and powertrain research and development. Between 2012 and 2014, Neil worked as the base engine development manager at Jaguar Land Rover. However, he returned to MAHLE Powertrain, and since 2017, he's been head of engineering over in Germany, where he has responsibility for all of the engineering activities, including thermal management systems developments, fuel cell powertrains as well. And Neil is qualified with a degree from the University of Hertfordshire and is also a chartered engineer. So over to Neil.
Good afternoon, ladies and gentlemen. Today I'm going to be presenting to you a presentation entitled Challenges and Solutions for Fuel Cell Thermal Management Systems. I'll be giving a brief overview of the specific challenges that arise in fuel cell vehicles, the approach that we have taken to understand these requirements, and then a few of the specific solutions that can be applied for a robust fuel cell thermal management system. A brief introduction as to who we, MAHLE Powertrain, are. Our history can be traced back to the road car engineering division of Cosworth. We were acquired by Audi in 1998 and then by MAHLE in 2005 to become MAHLE Powertrain. We have in excess of 60 years of experience within developing high efficiency internal combustion engines and associated powertrain integration, including then thermal management systems. And since our acquisition by MAHLE, we've also then developed extensive capabilities across all aspects of powertrain, including increasingly in fuel cell powertrains. In response to the global electrification trend, MAHLE Powertrain has developed a dual strategy to ensure continued optimization of both the traditional powertrain technologies, in addition to developing capabilities and solutions for the changing mobility world, within which we've been called include fuel cell powertrains. But what is clear is that thermal management systems sit firmly in the middle of both worlds, and if anything, play an increasingly important role in ensuring optimum powertrain performance, for example, when maximizing battery electric vehicle range under all real-world conditions. As is well known and discussed, the key driver for future powertrain development is coming from the goal of CO2 reduction and ultimately net zero CO2 emissions. In order to achieve this, our approach all along has been to use or propose the use of the most suitable and relevant technology for each application, and that the use case determines the ideal drivetrain. This figure shows a representation of the potential different solutions for the diverse requirements that come from the type of usage profile that the vehicle is going to be exposed to. As such, we do see fuel cell powertrains being a key part of a diverse future mobility, with particular application to larger passenger cars and heavy-duty vehicles. The ability to refuel quickly and the avoidance of large battery packs make the application of fuel cells in these scenarios ideal. Obviously, for this technology to become widespread, there are various challenges that need to become, which also then need political support to realise. So having set the scene as to where we see the ideal application for fuel cell powertrains, I'll now move on to some of the specific challenges that arise for thermal management systems when using fuel cells. On top of the usual technical challenges that need to be overcome when developing a thermal management system for any vehicle powertrain, there are some specific issues that relate to fuel cell vehicles, which I'll address some of these in the following slides, such as system complexity is increased compared to a typical combustion engine system, as is an increased specific heat rejection. Coolant conductivity and cathode air management are two particular points I'll address. Operating conditions such as cold start can present challenges, and this also has a large impact on the control system requirements, although I won't go into that today. And finally, one of the big challenges for fuel cell powertrains in general is the subject of cost, which then also puts pressure on ensuring that the solutions found to the individual thermal management challenges are also solved in the most efficient manner. In order to fully understand the specific challenges and to be able to develop the relevant solutions, the whole fuel cell systems needs to be understood. And so that has been the approach that we have taken. Based on our experience with powertrain systems development, we have then developed our processes further so that they can be applied to the specific case of fuel cell powertrains. Starting from the high-level requirements capture, we then further developed our analysis processes from the vehicle level to provide the high-level requirements, and then subsequently our 1D and 3D analysis tools to be able to model all aspects of the fuel cell powertrain. We have coupled this with developing further specific test processes and rigs, starting from component rigs through to thermal management test rigs, and then up to complete fuel cell powertrain test beds, so that the full interaction with the fuel cell can be understood. These facilities not only allow us to develop and validate systems, but then also provide the information to feed back into the analysis tools for further development. These are then all combined in testing in the vehicle to confirm that the initial requirements that were set have been fully realized. From this understanding, I'll now discuss some of the specific challenges and solutions, and the first point being the general system complexity. Here is a simplified schematic of a typical fuel cell powertrain thermal management system. The system is similar to what is seen in hybrid powertrain systems, with here 3 different temperature circuits to ensure the relevant components can be maintained at the corresponding temperatures. The high temperature circuit, which is used for the cooling of the fuel cell itself, with the maximum temperature typically being limited to around 85 degrees C, lower than for a combustion engine, with the fuel cell ideally running around 65 or 70 degrees. The low temperature circuit is required for the electrical components, including the additional fuel cell compressor and fuel cell DC-DC converter, and then a refrigerant circuit for the HVAC system and battery cooling. There are then also further additional components that form part of the system, such as the ion exchanger, the humidifier, the hydrogen heater, add further complexity. And if we were to consider heavy-duty powertrains as well, there could be 2 or 3 separate fuel cell systems that are combined and that all then need to be integrated and cooled. So to find the optimum configuration, the cooling system will be modelled, and in particular to ensure sufficient heat rejection in the most efficient manner. This chart shows a simplified representation to highlight the challenge of the increase in specific heat rejection when compared to a gasoline engine in this case. An example here based on a passenger car with a final 100 kilowatts of traction power. In order to supply this power to the wheels, initially we need more energy content in the fuel from the gasoline. And the significant difference we see in the energy flow is that the fact that a significant portion of the heat energy is lost to the exhaust with the combustion engine, which isn't the case with a fuel cell. And the end result is that most of the waste heat goes into the coolant in a fuel cell. We then end up with a similar order of magnitude of heat rejected into the coolant, but this needs to be dissipated from a lower temperature. This therefore means that the radiator-specific heat rejection required cooling performance is 1.5 to 2 times higher for a fuel cell powertrain. And if we were then to consider this for a heavy-duty application where the basis is a more efficient diesel engine, then this challenge increases further. This then places the requirement on the whole system layout to ensure sufficient cooling area and airflow. An additional point with fuel cell powertrains is the electrical conductivity of the coolant as it's flowing through the fuel cell itself. Conventional coolant becomes too electrically conductive during fuel cell operation, which comes then from various sources, either the ion contamination from bipolar plates, ion emission from the aluminium heat exchanger in the surface itself, or all of the components or the materials in contact with the coolant, or oxidation of the coolant itself. If the conductivity becomes too high, this causes various issues from damage to the fuel cell, reduction in stack efficiency, through to electrical shock hazards. And so this, from a legal point of view, needs to be minimised, but then also from a robustness point of view, needs to be minimised. For this, a specific fuel cell coolant will be used as opposed to the standard automotive coolant. But in addition to this, coating of the key components within the coolant circuit itself is carried out to prevent the emissions of ions or minimise the emissions of ions in the first place. A thorough understanding and selection of the materials used in all of the components that are in contact with the coolant is required in order to minimise the emissions. As I said, on top of the legal limits that need to be maintained, there's also then typical aim of trying to ensure a maximum amount of, say, 20 microsiemens per centimetre for robust operation. And as the aluminium heat exchangers are typically the largest surface area and contributors within the system, inner surface passivation is applied in order to reduce this impact. And the typical effect of this can be shown in the graph when we look at some results from component-specific testing. In addition to try and minimise the conductivity or ions that go into the circuit in the first place, additional measures such as ion exchanges are also incorporated into the circuit to ensure low conductivity in the coolant circuit over the whole vehicle life. Typically a bypass with a bypass so that the flow through the exchanger can be controlled depending on the operating conditions, and a portion of the coolant then will be passed through the ion exchanger to remove the ions and ensure the required levels of conductivity, and here levels less than 1 microsiemen per centimetre being achievable. This emission of ions is heavily dependent upon different factors such as lifetime, temperature, flow rate, etc. And so a thorough understanding of the system parameters and control is required to ensure that the conductivity can be kept at the required level. And then finally moving away from the main cooling circuit and then into the cathode air path, which is still a key part of thermal management. Similar to a combustion engine, the air path management into the fuel cell is critical to the efficient and durable operation of the fuel cell. Not only the temperature, but also the humidity is critical to the fuel cell. And the figure here shows the typical components in the cathode air path. So through the air filter, which has its own more extreme requirements, electric compressor, then into the charge air cooler, and then the additional humidifier that's required. It then flows through the fuel cell, back out through the humidifier, and then out of the exhaust. For the humidifier itself, there are different technologies that are applied, for example, hollow fibre membranes. Here's a concept with a flat, semi-permeable membrane that allows the exchange of humidity from the exhaust gas flow out of the stack to protect the fuel cell from drying out. The approach taken is that the two airflows, so the fresh and the wet air, flow through the stack without mixing. At the membrane surface itself, the humidity exchange takes place via diffusion. This process again needs to be carefully controlled to ensure that the humidity of the air into the fuel cell is kept at the right level. And so with the application and control of bypass valve to ensure that under all conditions, whether power output, ambient conditions, etc., the fuel cell is operating at its optimum. And so that then brings me to a summary of the quick short presentation. Here, just to summarise, we believe that the fuel cell powertrains do have a key role to play in the future mobility concepts. The fuel cells themselves present further thermal management system challenges compared to traditional powertrains, whether increased complexity or specific heat rejection, the coolant conductivity, or the air path management. But a complete system understanding allows specific tools, processes, and solutions to be developed to ensure cost-effective and robust production powertrains. And so, with the final slide, I'd like to thank you for your attention, and I look forward to the discussion at the end where you can submit your questions in the chat. Thank you very much.
So thank you, Neil, for an excellent presentation there. A really useful summary from a systems integration point of view. We're now going to move on to a specific case study. So if we could pop to the next slide, please. So the next presentation is entitled Project Use and specifically thermal management. And this will be presented by Pratap Rama. Pratap is the fuel cell powertrain manager at Jaguar Land Rover. Since beginning his work on hydrogen-fueled automotive fuel cells in 2002, Pratap has covered the topics of fluid and thermal management across cell through to system level development. He's currently responsible for managing the development of a fuel cell powertrain capability as part of the Zeus project, which is funded through the Advanced Propulsion Centre. Pratap holds a PhD in fuel cell engineering from Loughborough, an MBA from Warwick, and is a chartered engineer. So I'll pass you over to Pratap.
Hello everybody, my name is Pratap Rama. I'm the group leader of the Hydrogen Power Pack at Jaguar Land Rover. This covers the fuel cell system, the energy storage system, the high voltage electrical distribution and primary cooling system. Our lead engineer for the cooling system integration is Tarrant Ark. He covers the design and integration of all cooling circuits within the vehicle system, including the development of the thermal management system and design validation. Our work is headed by Ralph Clegg. He's the head of hydrogen and fuel cells, and he leads the assimilation of both the onboard and offboard hydrogen technology into engineering and indeed the wider business here at Jaguar Land Rover. So in this presentation, I'll cover a short introduction to the APC-funded Zeus project. I'll cover the technical objectives and the funded partners. And the second part of the presentation discusses the pivotal topic of thermal management in fuel cells, in fuel cell vehicles. And it is pivotal because it's one of the most important factors that governs what power output can be achieved in premium automotive applications. I'll briefly examine this through a holistic view of thermal management requirements for automotive fuel cells, and a conceptual trade-off on radiator performance. So in February of this year, Thierry Bolloré, our CEO, announced a new global strategy called Reimagine. This focuses on a strategy towards zero net carbon emissions by 2039 across our supply chain, our products and our operations. This includes the electrification of Jaguar as a luxury brand by 2025, with pure EV variants of Land Rover SUVs coming through by 2024. The business is also preparing for the adoption of clean fuel cell power with a maturing hydrogen economy. So technically, why are Jaguar Land Rover looking at fuel cells? There's loads of reasons, really, but the key reason is our customer-first focus. For our heaviest SUVs, our signature above and beyond performance means a wide environmental operating range, and this includes towing capability, speed, vehicle range, and fast refueling. And this really becomes difficult to achieve for zero tailpipe vehicles with battery-only powertrains. For a fuel cell powertrain, we can expect reliable sub-zero performance, including unassisted start from as low as -30, instant power and heat, depending on water management, 5 minutes refuel, and we can sustain peak power for longer. And this is extremely important for towing capability and sustain maximum speed capability. The lighter powertrain also means improved dynamic performance, higher payload capacity, and from a supply chain point of view, a lower cost to ship power pack parts around. The graph above, it looks at where mass parity is met versus a pure BEV configuration for two different mass scenarios. So in the 2021 scenario, current case, we see that the mass parity is achieved at about 55 kilowatt hours. And if we take future projections looking at the 2030 horizon, then we see that mass parity is achieved at about 85 kilowatt hours. It's worth noting that when we look at the fuel cell, it's not just the fuel cell, it includes a 15 kilowatt hour high output capacity HV battery. It also includes a DC-DC converter and 100 kilowatt net fuel cell power 100 kilowatt net power fuel cell dressed engine. And obviously the onboard hydrogen storage system is sized according to the kilowatt hour target. Effectively, what this says is that yes, where a lot of energy is needed, hydrogen fuel cell power packs are a lighter option. Of course, for heavy SUVs with signature performance, the onboard energy requirement can easily exceed the 85 kilowatt hour requirement. So to accelerate vehicle development work, we successfully attracted government funding last year through the APC project. Without funding, development would have happened more slowly and on a piecemeal basis. So it is an important project. The technical objective is to demonstrate vehicle attributes, including long range, quick refuel, towing capability, and high and low temperature performance. And central to the project is this unique cooling system designed by Marelli Automotive Systems. Just to talk a little bit about the scope of the project and the project partners. Obviously, Jaguar Land Rover, we do the vehicle level integration. Delta Motorsport are providing the high voltage energy storage system. Marelli Automotive providing the primary cooling radiator. This includes production trials, radiator concept design, detail design work, and hardware performance evaluation. AVL Powertrain UK Limited as well on control integration, and UK BIC as well, who focus on the industrialization of the HV high voltage energy storage system. So that's project's use. So let's start off by reviewing some of the top level requirements for fuel cell primary cooling in automotive applications. The top host temperature for a fuel cell is typically limited to around 95 degrees peak. Sustaining operation at that point becomes a challenge because it can compromise stack durability. So the rated power is usually around 85 degrees. And the challenge here is, being able to reject the heat at this lower temperature compared to where IC engines operate. Also, it's worth noting that there's minimal heat loss through the exhaust for a fuel cell system, unlike an IC engine. So the one-third principle doesn't apply. The heat is principally rejected through the radiator system. The stack can typically tolerate a delta T of about 10 degrees, which drives a high cooling flow rate requirement, typically around 200 liters per minute for a prime mover fuel cell system. The coolant conductivity itself has to be suppressed to about 10 microsiemens or lower, and this affects things like material selection. So we have to be careful about what kind of materials, what kind of metals we use, but also plastic parts as well, and hose materials. From a production point of view, this brings certain requirements, and for certain applications, a coating requirement might be introduced. From a thermal shock point of view, we have to ensure that end tanks have been designed for thermal expansion, and we have to balance the duty on the front and the rear pass. From a vibration point of view, we have to make sure that the end tanks have been designed to support features that tolerate movement in 3 axes. And one of the key topics is that we've got to make sure that we've got good airflow distribution. So, we need to carefully consider fan matching and carefully consider airside blockages. We'll just take a side step here for a second and look at the US DOE target for heat rejection. And this is pegged to an 80 kilowatt net power fuel cell system. So what this shows us is that the less efficient the cell and the lower the stack operating temperature, the more heat you need to reject per degree. So this 1.45 figure is, the total heat normalized to the extreme temperature difference. And the higher the figure, the larger the challenge for the radiator and fan pack to satisfy the airside thermal performance requirement. It's a fairly straightforward analysis, but it simply illustrates quite well the need for good cell performance and the ability to sustain operation at higher temperatures for hot ambient operation. So we can move into the conceptual trade-off study now. For the purposes of the analysis here, we're basing it loosely on the Davis dam test. So why Davis dam? Well, it's a really important test because it drives the sizing of the powertrain for large SUVs. The speed time profile means that high power at high ambient temperature is required, and with the vehicle at its gross towing weight. This is done at an ambient temperature of about 40 degrees. The SAE standard stipulates a 40 mile per hour requirement as minimum speed, although obviously at Jaguar Land Rover we target a much higher speed figure. But based on this type of test, we can look at the trade-off in heat rejection and the airside pressure drop for a twin pass radiator pack. For the work presented here, this is done at 3 standard fin densities. We simply refer to it here as high, medium, and low. And the high fin density has the higher UA value. So the simple question we're trying to answer here is, how is heat rejection affected by different configurations, and what happens when we consider cooling airflow versus vehicle speed? So this here is the bulk output. On the x-axis of these 2 graphs, we're looking at different radiator combinations. So the first 3 looks at single pass with the high, medium, and low fin density. And then we're looking at different combinations of twin pass configurations. So the assumption here is that the inlet pass, or the first pass, is where the hottest coolant, top hose out, is meeting the coldest air, the inlet air, and the second pass is the outlet. The first graph on the y-axis is looking at heat rejection as a percentage of the heat rejection required for maximum fuel cell power. And on the second graph at the bottom, we're looking at the pressure drop as a percentage of the maximum pressurized capability of the fan, and that's under ideal conditions. So it's a simple setup, no Rama air effect and no airside blockages. It's a conceptual trade-off. So again, we're using this to illustrate the qualitatively the relationship between airside heat rejection performance and pressure drop. So let's take the first of these to begin with, where we're looking at a single pass. Here we see that the higher fin density improves the heat rejection capability as the airside heat transfer improves, but this happens at the cost of airside pressure drop. We note here, though, that with a single pass, we don't meet the heat rejection required to be able to achieve maximum power from the fuel cell stack. So we then consider a twin pass configuration, and here we're looking at a high fin density radiator as the first pass at the front, and then different options for the second pass: a high fin density, medium fin density, and a low fin density. And here we see that the heat rejection performance is being met, so we can unlock that peak electrical power capability from the stack. And we also notice that the front radiator is doing most of the work, in excess of 85% here, for example, and the second pass is doing the rest. But also we see a ratiometric increase in the airside pressure drop, so we see the penalty starting to come through on the air side. So next we retain the twin pass configuration, but we've changed the front pass to a medium fin density radiator. And here we see that the pressure drop starts to reduce and the thermal balance starts to shift a little bit. So we see that the front pass is now doing less than 80% of the thermal duty. And the final step here is to change the front pass to a low fin density radiator. And now we see that the duty on the front pass is reduced to about 75%. And the airside pressure drop has improved on a back-to-back basis. The better thermal balance is good because it reduces the thermal shock, and therefore we can improve the durability of the radiator pack overall. But this conceptual trade-off analysis gives us a good insight into that, that trade-off between the heat rejection and the airside pressure drop. And importantly, the analysis reveals that the airside pressure drop, presents a significant challenge, a good challenge to, fuel cell integration. The simplification so far has been that in the treatments of the air side, and we can look at that a little bit more closely on the next slide. So here we're now looking at a conventional vehicle packaging arrangement and the actual airflow achieved as a function of vehicle speed. For the x-axis, we're looking at vehicle speed, and on the y-axis, we're looking at the airspeed achieved as a percentage of that required for full heat rejection at maximum fuel cell power. So what this shows is that without air path optimization, it's difficult to maintain heat rejection performance at low vehicle speeds. And this realization therefore drives a different development path for thermal management in premium fuel cell vehicles. It's an important conclusion. It conceptually illustrates the engineering challenge for fuel cells aiming to fully exploit the benefits of hydrogen technology. The larger fuel cell system essentially reduces the size of the battery system, and it's a key enabler to access the benefits of a lighter powertrain and a greater vehicle range. But the accessible power can be constrained by the heat rejection capability, as we see, for the radiator system. So, in practical designs, therefore, we've got to achieve a careful balance so that we can meet the heat rejection requirement, but also have a radiator system that's manufacturable. And essentially, this is what JLR and our project partners are currently working on through the Zeus project. It's a rich topic indeed, and a fertile ground for innovation, and a very exciting area of activity within the Zeus project itself. So just to recap, the Zeus project sets out to deliver a premium fuel cell SUV concept. Participation in the project has given the partnership the chance to grow its design and manufacturing capability for the automotive fuel cell market, and the learning is indeed helping the consortium to get a competitive edge. We also see that if the project is successful, there are significant exploitation opportunities in adjacent fields. From a thermal management point of view, we had a short discussion on the fuel cell cooling requirements and how they drive unique design considerations. And we saw the importance of vehicle thermal management to fully exploit the technical benefits of fuel cells for premium vehicle applications. So with that, I draw this presentation to a close, and I would just like to thank our colleagues, including our project partners at Marelli. So thank you for your attention, and I hope that was useful to everybody.
So thank you, Pratap, for a very informative presentation, certainly on the concept trade-offs that need to be considered. So the last presentation for today is entitled Thermal Management for Multiple Fuel Cell Stacks Applied to Both Terrestrial and Aerospace Applications. And the presenter is Dr. Cedric Rouaud, who is a global technical expert at Ricardo. So Cedric has been global technical expert in thermal systems for FCEVs since 2017, and is now the R&D fuel cell leader for Ricardo. He's working on several applications across the sectors that cover passenger cars, commercial vehicles, marine, railway, stationary power generation, and also aerospace. And his work covers the development of all of the key subsystems, so the battery, the electric machine, the power electronics, the fuel cell, and particularly their integration from a systems perspective. Cedric joined Ricardo in 2008 as a principal engineer in the thermal group, and between 2011 and 17, he was chief engineer for powertrain development and thermal management. He began his career at Renault as a research engineer in thermal management, also looking at FCEVs, while fulfilling his doctorate at the University of Poitiers on thermal management of a hybrid electric vehicle. So I'll now pass you over to Cedric.
Thank you, Alistair. and good morning and good afternoon, everyone. I will be happy to present you today thermal management for multiple fuel cell stacks applied to terrestrial and aerospace applications. But first, we will go through the thermal management requirements for fuel cells compared to combustion engines. So we see here that even if the fuel cell stack is higher efficiency than ICE diesel for truck applications, ICE meaning internal combustion engine, we notice the heat reaction is much higher for the fuel cell than the engine. So for a 250 kilowatt fuel cell stack, we can get roughly 250 kilowatts of heat rejection. The heat needs also to be rejected at to ambient at lower temperature, which lead to radiator specifications that are bigger than internal combustion engine applications, and also the fan cooling size is higher than engine applications. The pumps, fans need to be electrical as well. We need also to take into account the cooling and heating requirements for all the electrical components, electric motor, power electronics, the battery, and even the cabin thermal comfort. So all these requirements need specific control as well, which lead to a bit more complexity when we're developing fuel cell systems. Also, in the thermal management area, there's a challenge in the development of the balance of plant or balance of system that we have around the stack, which is the core of the fuel cell. In the case of large applications, we can go into multiple stacks. So that means that we start from passenger car applications at 120, 140 kilowatt electrical power, and moving on to 250 kilowatt, for example, with two stacks at least, that can be arranged in parallel or series electrically. The stacks would require a hydrogen loop, air loop, and cooling circuit loops combined together between the different stacks in order to be able to minimize the cost, the weight, and volume of the balance of plant, instead of designing a balance of plant reusing the same balance of plant for each stack as it is done on the conventional applications nowadays. Each fluid loop has got pumps, valves, injector, and air and coolant loop. I've got also heat exchangers. For example, we have a humidifier, charge air cooler on the air side, and a radiator on the coolant side. The air at the cathode needs also an electric compressor. It is important to control the stoichiometry and relative humidity together with pressure, temperature, and mass flow rate of fluids at the anode and cathode to reach good durability and efficiency. All this is part of what I call the thermal management of the fuel cell system. Even if it implies electrochemical expertise in the stack, the rest of the balance of plant system is coming to thermal, hydraulic, aerolic, and also electrical domains. So when focusing on the thermal management of the fuel cell system, so we can have a holistic approach of the thermal management. Instead of having a consideration for the low temperature circuit for the electric drive, the very low temperature circuit for the battery, and the fuel cell in isolation, we tend to combine all together. And this is an example on the left-hand side of integrated thermal management, ITM, that is being developed using model-based development, another acronym MBD. We come to that more complex solutions of combining the systems using heat exchangers between the cooling circuit that are usually separated, or valves between the cooling circuits that use the same cooling fluid, because of the benefit in terms of reusing the waste heat from certain components to warm up others, and also the possibility to reuse the radiators that are not being used fully at certain operating conditions or ambient temperature. With this holistic approach, we can claim some benefits in terms of EV range improvement and even hydrogen consumption, up to 25%, depending on the operating conditions. It helps also to manage the heat reaction better within the packaging and NVH constraints. The model-based development also is helping to reduce the cost and the time to develop such complex cooling circuit layout by up to 30%. We present here an example of 3D CFD analysis on a project that has been run for Toyota and Kenworth, and that's public domain information, mentioning that it was important to assess the airflow rate across the main cooling pack and also on the side radiators because of the high amount of heat that needs to be rejected by the fuel cell during maximum operating conditions, maximum load. So this 3D CFD helps to minimize also to the minimum required, the cooling fan power and size, and also to develop additional heat exchangers that are not usually used on conventional diesel engines on truck applications. The organization of the fans on the cooling structure, the cooling heat exchanger, is also important because we have not got a mechanical fan anymore like on a diesel engine, but we use smaller electric fans, 48 volts, for example, in this example, with an array of 4 and 2 fans per radiators. So again, the thermal management here helps a lot with the integration of the fuel cell on the vehicle. I mentioned already the balance of plant. So when we look at how to develop a balance of plant with how to size pumps, blower, compressor, valves, injector, charger, cooler, humidifier, and radiator, we would like to use a process that is helping to get to the right layout of the balance of plant, which could be complex when we have multiple stacks on large applications, not only for high performance cars, I would say. The conventional cars have got only one stack, but when we move on to high performance cars or large applications such as trucks, railway, marine, or aerospace, we use the process described here. We start on the left-hand side from defining the system boundaries and the targets settings, going to the prioritization of the balance of plant function, and including not only the heating, cooling, dehumidifying or humidifying functions, but also the cost. And with this, we use tools such as architecture-independent modeling to size the fuel cell versus the battery pack first, before going to the definition of the balance of plant using a Ricardo Fuel Cell Architect tool that I will present you later today. With this, we go into now analysis of the performance versus the targets using an energy balance approach for sizing also and specifying each component of the balance of plant. Before moving on into a more detailed design and more refinement of the balance of plant components using 1D tools such as AMSIM or Gamma Technology or Ricardo Ignite based on OpenModelica. And with this 1D model that can operate in transient during different operating conditions and ambient conditions, we can go into reduced order models that can be used into advanced control techniques such as model predictive control using satellite navigation information, what we call electronic horizon, in order to operate all the ancillaries at their best operating point because we will know what will happen next. All this put together from the hardware to the software will bring a benefit to our customers of 5 to 15% hydrogen consumption less. So at Ricardo, we designed the balance of plant through our modeling tool called Ricardo Fuel Cell Architect. So we begin by gathering a specific minimum set of input requirements in agreement with the end product seen with our customer. The tool then uses a database of fuel cell components, which is continuously updated with the different discussions we have with suppliers under NDA, of course, so the database is not to be used externally. But this database provides the model with attribute information together with performance at specified rating conditions. The model is fed with a set of template architectures, which are based on Ricardo experience and literature analysis. And within the model, we have templates that can be used for a variety of functional solutions and tested against input requirements, which can lead to system-level performance and attribute estimates. So we have viable solutions from the model that are collated and evaluated with learning fed back to the template architectures. Finally, the down selection on the left-hand side process leads to a small set of concept schematics of the layouts of the balance of plant, which are drawn up in detail for wider engineering assessment. So many of the functional requirements of the fuel cell balance of plant are highlighted here in the different colors: blue for the anode, green for the cathode, and red for the coolant. So we have different similarities between the specific functions. So regulate the flow rate, control the pressure. The solutions can be although different due to the specific performance requirements for each circuit. For the hydrogen loop, the blue one, the air loop, the green one, and the coolant loop, the red one. So also we have functions that can involve multiple fluids, such as the dilution of the purge gas exhaust with the cathode exhaust to minimize the hydrogen concentration at the system outlet. So an understanding of all the potential functional solutions is necessary to find an optimal system solutions. With so many functions, it is necessary, of course, to simplify the down selection task to avoid different iterations in the design. So we use a subsystem grouping approach, which links highly coupled functions. So the Fuel Cell Architect tool allows to rapidly explore different alternatives to each functional group to find optimal real-world component solution. So the prime solution from the Fuel Cell Architect tool are evaluated manually through Pug matrices to weight up attribute, performance, and component technology readiness levels. And step by step, we resolve the architectural options down to one or two preferred solutions for detailed engineering and supplier liaison, meaning when we go into the 1D analysis with the transient operation and the control activities. So finally, at the core of the Fuel Cell Architect, there is a model that is constructed to draw energy and mass balance, which is in the middle here, blurred. That was on the example of the Fraser project that has been presented to a webinar in May. The model provides interface conditions through the system at critical steady state design points. So the transient analysis and transient energy balance will be done in the 1D phase of the project. So also the model can produce Sankey diagrams for power flow analysis to help the verification and to understand why some solutions lead to higher efficiency and how we can improve that step by step before going into definitive design. Finally, I wanted to highlight one example again that we have presented into a webinar in May for an aerospace applications. So it's not exactly the main application that we discussed in IMechE, but it's we think a great example of how much we can stretch and push the development of the balance of plant and the fuel cell system. So we have here the different challenges that we have usually on fuel cell system development. With the high specific power, gravimetric and volumetric, it's even more important for aerospace application, but it's also very important on passenger car and truck applications, for example. The testing, when we have large applications, is also very important. And we have facilities in Ricardo that will be ready in Q1 2022 for up to 400 kilowatt fuel cell tests. The performance across full environmental range assessment using the model-based development, 0D and 1D, is very important. The same as the fuel cell stack selection and all the suppliers selections for developing the best of the fuel cell system in terms of performance and weight. The transient response, finally, is also important, and for that we use a 1D modeling techniques that has not been presented today, but can be developed further in the Q&A session, certainly. So with all this, we tick the boxes of all the challenges, and we can even highlight in that spider chart where we should be on an aerospace project compared to automotive project that will be in 2024, sorry, that will show best performance and lower weight for all the different operating conditions we can encounter in real life. On that note, I would like to thank you, and we can discuss in the Q&A session further. Thank you.
So thank you, Cedric, for a very informative presentation there that certainly shows some of the complex interactions that can occur with managing fuel cell thermal management. So that's an excellent way to wrap up the formal presentations. We're actually running slightly out of time, but what I would like to do is just open up for 7 minutes or so some questions, so that we can pick up some of the questions. I can see that you've been typing in the chat there to give our speakers a chance to reply. I apologise if we don't get through all of your questions, but of course you can reach out to any of the speakers who are here today. I'm sure they'll be happy to answer further questions. So I'm just going to go through a few questions in order. The first one is from Jerome from Tata Technologies, and he's asking, is the water generated by the fuel cell, can that be used for the thermal management of the fuel cell itself? Now, I think, Neil, you touched upon that being used in the air path, did you, Neil? So I don't know if you're muted or not, Neil. No, we're struggling here. Or Cedric, is that something that you think could be incorporated in the future?
Sorry, Alistair, can you ask again the question? Sorry, I thought it was one minute.
Yeah, sure. It's a question from Tata Technologies from Jerome. He's asking if the water that's actually generated by the stack could be used in turn for the thermal management of the cell.
Yes, it is in a way, because we humidify the cathode inlet by using the water that is generated by the cathode. So this is why there's a humidifier. Neil mentioned that, and I mentioned that as well. Also, the water can be used potentially for other applications. You might think about for the petrol heads. Why not reuse a tank of water to cool a heat exchanger, like spraying on a radiator, like it was done on Subaru sporty gasoline engines in the past. So that's a possibility.
Yeah. Thanks, Cedric.
Hi, Al. Can you hear me now?
I can. Yes. Hi.
Okay, I'm back in. Yeah, as I just add in. Yeah, I think as Cedric said, yeah, there's various ways. I think, as I mentioned in the presentation, so humidity control is key for a fuel cell, not just from the thermal management point of view, but just the degradation and performance point of view. And so that's where a key part of the sort of the water is then recycled and then controlled to maintain that humidity depending on the operating point.
Thanks, Neil. So exhaust gas recirculation isn't dead after all then. That's good to hear. So if we move on into the next one, so this is from Simon Petrovich. And Simon's asking, what is the overall well-to-wheel efficiency for a fuel cell electric vehicle? Don't know if any of you wanted to pick up on that one.
So yeah, I think overall well-to-wheel efficiency is a difficult, let's say, question to answer. It depends, I think, in terms of, let's say, environmental impact, not efficiency, but well-to-wheel emissions. It depends, of course, heavily on the electricity produced to do the electrolysis and to generate hydrogen. Hydrogen can also be made as a byproduct from industrial processes, in which case it's nearly free, depending, of course, on your reference. So I don't think it's an easy question to answer in this forum. But definitely with renewable energy, the environmental impact is less than, for example, diesel or gasoline.
Thanks, Nick. And I think you've hit on a very important point there, which is the energy storage aspect of it all. So, potentially using renewables to generate hydrogen off peak, maybe store it as ammonia and convert it back has even been talked about. So thanks for
exactly.
that.
So being able to use renewable energies in periods where the demand is not high and storing that energy is something that we could not do with pure electricity, or not as easy. We would need to go through something like hydrogen or ammonia or something else.
Thanks, Nick. Makes sense. One other question for you, Nick, was from Stanley, and he was asking if Toyota is also investigating a hydrogen internal combustion engine.
Yeah, so I think I answered that question. So we are, of course, also investigating hydrogen combustion. We think it has its place, especially maybe on the short term. There are some applications where it makes sense. We have actually demoed a hydrogen combustion engine in a 24-hour Fuji Speedway race just last month. So definitely something that Toyota is also investigating.
Thanks, Nick. So we'll move on to a question from William from JCB. And William was asking about the application of fuel cells in the likes of mobile agriculture applications, where you're obviously in relatively dirty conditions or dusty conditions, high ambient temperature. So how significant is the hydrogen purity to the fuel cell efficiency degradation under sustained high load under those sort of conditions? If anybody wants to chip in on that one.
Yeah, maybe I can answer that as well. So hydrogen purity is very essential to the fuel cell lifetime. There are various standards, so you need quite pure hydrogen for use in the fuel cells that we have on the market right now. So definitely you'd need to comply with the standards for fuel. In terms of the dust, I think you have similar problems with conventional combustion engines. You would still need to size your powertrain cooling system appropriately, considering the dust. So I think similar, let's say, challenges are there. But definitely the cooling challenge requirements for the cooling requirements for fuel cells are larger in terms of cooling system. So you'd need to have to take that into account.
Yeah, I think Al as well. I think the air filtration is a big issue anyway, not necessarily just thermal management, but then the air filtration, even for the passenger car or fuel cells, is sort of like the additional gases that need to be filtered or processed. There's a big increase over what you'd need for a combustion engine as well. And so obviously in an environment like that, the air filtration requirements are significantly higher.
Thanks, Neil. And presumably that has a knock-on effect on even things like servicing, does it?
Yeah, exactly. Yeah, you need to obviously then sizing of the filter if you need to meet the requirements. So yeah, the whole, again, it's another sort of system impact that needs to be considered. And so you end up then with different harmful gas absorption on the filters, so not just dust and particles. You're also trying to take out some of the harmful gases as well. Yeah.
Thanks, Neil. And Nick, thank you for that. I am conscious of time, but we've got time for one more question, I think. And this is from Wei Wu, who asks, it's a nice one to finish on. How could the waste heat from a fuel cell be reused in some shape or form? Are we aware of any technologies where that's viable? So I think that's a sort of systems-based question that's maybe relevant to, I know Cedric, you've got a lot of interest in waste heat recovery. Maybe you'd like to have a go at that one.
That's correct, Alistair. Thank you. So the different, can you hear me?
Yes, can hear you. Yeah.
Alistair? Yeah, okay. So I was saying that the way to recover the waste heat, there is one obvious one. It's the small amount of heat that is left and pressure of air at the back of the cathode using a electric turbine. That is a possibility, but you need to manage, of course, the vapor and liquid content into the vapor. So that means that to avoid damaging the turbine blades. Other forms are in also what we envisage is using organic Rankine cycle, like we did for conventional internal combustion engines on the cooling circuit heat source. That means that we use an organic Rankine cycle circuit plugged on instead of the radiator, and the ORC will cool the the fuel cell. That's, I would say, quite innovative or disruptive. It's not yet done on the market, but there are different attempts to recover the huge amount of heat that we have mentioned in all our presentations today. Even if it is at a low grade heat, 80 degrees Celsius, there is still good potential for that recovery.
Brilliant. Thank you.
We certainly see a good opportunity. Sorry.
Go on, Pratap. Yeah, sure.
Yeah, apologies. Yeah, we certainly see a good opportunity with that heat for cabin heating, for example, and especially under cold start conditions where the battery's got its own limitations. So yeah, recovery of that waste heat under cold start conditions is it's an excellent selling point for fuel cells, and helps to deliver a better sort of customer proposal, let's say, for sub-zero operation.
Yeah. Good stuff. We'll finish just on one other question, Pratap, while we've got you on the mic, because it was an interesting one, and it's from Jack from Diamond Hard Surfaces. He mentions that in your presentation there was a mention of a coating potentially required on the fuel cell with regards to coolant conductivity suppression, and he was just asking what sort of coatings those might be.
Oh, proprietary. There's been some work on left field applications, basically, and they found their way into fuel cell applications. It's possible to find these out, but I guess it suffices to say it's not a traditional surface coating. It's more of a conversion, and I think there's a couple of key principles, basically, and it's not. I'd say it's not a firm requirement because there's, if you can manage the production process and the after treatment, the cleaning process for the radiator pack, it's not absolutely necessary, but it certainly can help from a servicing point of view, because if you in lieu of the coating, you have more aggressive servicing requirements around the cooling and the DI filter. So yeah, there are advantages to having the coating, but yeah, as I say, it's not a conventional surface coating. It's more of a conversion.
Yeah, understood.
I think maybe Neil can probably elaborate better than me, but yes, there's different options available.
Great, gents, we're out of time, unfortunately. I think we could keep going all afternoon, but so. Firstly, thank you for your excellent presentations. Really enjoyed them. I think the takeaway point is that the challenges across thermal management are larger than ever. It doesn't matter what powertrain you're looking at, they've all got thermal challenges. And what's interesting going forward is to see how the systems integration part plays out. Potentially with fuel cells integrating the thermal management of the electric motor, etc., into a common circuit. So thank you very much for those excellent presentations, much appreciated. A lot of effort has gone into that. I'd also like to thank Fiona and the team at the IMechE for helping the webinar to go very smoothly. There's no issues. And last but not least, I'd like to thank all of you for attending and just give you a reminder that there will be a face-to-face conference this time next year, around about June in the UK. So if you've enjoyed this webinar, please do keep an eye on the IMechE website, because fuel cells will be just one theme that we're looking at in that conference next year. We look across the powertrain, all different systems. And please do reach out to the presenters if we haven't managed to answer all of your questions today. So that brings the session to a formal close, and I'd just like to wish you all a pleasant afternoon, hopefully with some sunshine, and thank you for attending.